Hello again, folks. Let's go ahead and finish our lesson. So let me share my screen. Let's get this out of the way. Okay, so the next thing we need to talk about is intersections of lines and planes. So recall that a system of equations is two or more equations containing two or more of the same variables. The coordinates of the solution to the system satisfy all equations in the system. These coordinates also locate the point where the graphs of the equations of the systems intersect. So if you remember, if we took systems of equations in algebra, you take two equations and you solve them, the answer to both equations, what x and what y are, is this point where they intersect. That works for any number of equations. So if we have three equations and two variables, they would still intersect right here, okay? Depending on if we're solving for that, okay? So an intersection is the set of all points of two or more figures. The intersection is the set of all points that two or more figures have in common. The next two postulates describe intersections involving lines and planes. Add these postulates to the theorems and postulates section of your math notebook. Okay. There's a couple, actually there's only two postulates here. First postulate is if two lines intersect, then they intersect at exactly one point. So you have two lines here. If they intersect, they will only ever intersect at one point. You cannot have two lines intersect at more than one point, except for if they intersect at all points, but we'll talk about that later. If two planes intersect, then they intersect in exactly one line. So this red line is the intersection of two planes. Think about it like two pieces of paper that are crossing each other. They would cross at this line. This is the place where all of the points on this line would be in both planes, okay? So add that to your postulate section of your notebook. And let's keep going here. Okay, here's a little bit more about points, lines, and planes and their intersections. So if you have the intersection of planes, we want to talk about these questions. Name the intersection of plane BCD and CFG. So BCD, that means that plane is on top. That's the top plane. CFG, that's this side plane. So if you have the two sides of the box, the top side or the top and the side, they will intersect right here. Well, that is line CD. Okay, and here's a visualization of that. You've got the top and the side. Well, they intersect right here at this line CD. Now, this is in Schoology. If you were writing this on this piece of paper, you would put a line segment line on top of that to denote that it's a line segment, okay? Down here, here's another question. What lines are skew to AD? Skew is a different word, one that we haven't learned yet. It says solutions, skew lines are different than planes, skew lines are on different planes and do not intersect, sorry. So this means that HE and segment FG and segment EF and segment BE and segment CF are all skewed to line AD. So we look at line AD. On this shape, we are looking for all lines that will never intersect with this line. Okay, so you've got HE, that will never intersect, so that's a skew line to AD. Got this one on the back side there, this one here, this one here, this one here. Now, if you really want to challenge, there are actually more lines that are listed here. But just like we talked about before, there are some times when it won't be listed and yet it still exists. For example, one line would be F. The line that goes diagonally through that won't ever intersect with AD. So technically HF is also a skew line to AD. And there's a few more. See if you can write down a couple more. That's just a challenge. Okay. Question 3. Name the intersection of HG and FG. So HG is the pink line here. FG is the purple line. So those two lines would intersect at point G. Whenever you are looking at shapes like this, it's always helpful if you can add some color to it. Draw it on your own piece of paper, color in a side, use your computer, see if you can find the highlighter function. But when you can illustrate them like this, it's a whole lot easier to use. Okay, I'll show you more about that another time. Okay, so let's keep going. We got more vocabulary. So this goes in the vocabulary section of your notes. Okay. We need to look at some special types of lines: parallel lines, perpendicular lines, and skew lines. Parallel lines are coplanar lines that never intersect. So coplanar, remember, coplanar means in the same plane. They're on the same piece of paper, and they never intersect. This arrow on both lines denotes that they are parallel. Okay. This little symbol is how we write it. Then we got perpendicular lines. Here's the little symbol for it. In your diagram, you can see it by the right angle. Perpendicular lines intersect at 90-degree angles. So if this angle is 90 degrees, what do you expect these ones to be? It's a little challenge for you later, but they would also be 90 degrees. Here's the next one, skew lines. We just talked about skew lines. Skew lines are not in the same plane. They're not parallel, and they never intersect. Here's a red line that goes right through that shape. Here's a blue line that goes right through that shape. They will never intersect, so they are skew. Okay. Last one is parallel planes. Parallel planes are planes that never intersect. Plane ABC is parallel to plane DEF. So it's like sheets of paper that are stacked. They will never intersect anywhere. So they're parallel planes. Okay, here's a little bit more about skew lines and parallel lines. What if you were given a pair of lines that never intersect and were asked to describe them? What terminology would you use? After investigating this subject, you will be able to define terms for parallel lines and skew lines. So parallel lines are two or more lines that are in the same plane and never intersect. Show lines that are parallel, to show lines are parallel, oh my gosh, to show lines are parallel, arrows are used. In the figure, AB and MN are parallel. So this is just another example. And here's another example of skew lines. I'll let you read that if you would like. You can pause and read it. Now down here, this is a little video that explains a little bit more about skew lines. So hang on just a second. Let me make sure I'm sharing my audio. And let's watch this video.
What are skew lines? To see skew lines, let's take a minute to explore the figure that's on the board. Well, as we can see, we have a few planes identified, and we have two lines identified as well. Here we have line L, and here we have line M. Let's take a minute and look at these lines. First, line L. Line L runs in two planes. If we look, we can see that line L is in plane A, this plane in the front. And line L also runs in this plane on the side. That's identified as plane B. So, we have line L, and line L runs in two planes. Planes A and B. Great. Now let's take a look at line M. Again, here's line M, And line M runs in two planes as well. This plane on the top, which is labeled as plane C, and this plane on the side, which is plane D. So we have our other line, line M, and that line runs in two planes as well. It runs in plane C and D. Now look, our two lines do not share any of the same planes. Now, in addition to not being in the same planes, if we take lines L and M and extend them out in both directions forever, we will see that they will never intersect one another. So, they're in different planes and they never intersect. These two lines are skew lines. Skew lines are lines that are in different planes and never intersect one another. So, we have lines that sit in different planes, and in addition, they never intersect one another. Now, don't confuse skew lines with parallel lines. They're different. Remember, parallel lines never intersect, but they lie in the same plane. To see some parallel lines, let's draw another line in this figure. Let's draw this line right here. We'll label this line, line P. Now let's look at the planes that line P is in. Well, line P runs in this plane in the front, plane A. And it also runs in this plane on the side, plane D. So our third line, line P, runs in two planes. It runs in planes A and D. Now take a look at our lines. Line L and P both run in plane A. They share a same plane. And if we take a look, extending out lines L and P, we can see that when we extend them out forever, they will never intersect. Since lines L and P are in the same plane and they never intersect one another, that means that lines L and P are parallel lines. Now, lines L and M are in different planes, and they never intersect one another. Since lines L and M lie in different planes and never intersect, those two lines are skew lines.
So that gave you a little bit of a different idea. She talked about them running in planes, the two planes they run in, which is a great way to think about how to identify skew lines. Now, something that personally annoyed me is that she writes crooked. I don't know if you noticed that, but another explanation there for you. Now your next objective is to go practice identifying skew lines. I will post this, but this is not going to be one of your assignments. So just go practice here. So this will be posted in Google Classroom. It's not right there right now. I forgot to post it, but it will be there when this video goes up. So let's see here. What's it going to show us? So it says in a triangular prism below, which lines are intersecting? ST and VW. Let's see if I can annotate this a little bit. Let's draw. So I've got ST, so that's this line, and VW, that's this line. So nope, not those. I don't know how to change my color. Hang on just a second. Oh, here we go. Okay. SV and UX. So SV and UX. So nope, those don't intersect. Let's pick another color here. ST and TW. ST is this one again. And TW. Oh, those definitely intersect. They intersect right here. So that would be our answer. you're going to practice the same thing. Okay. I need to erase my annotations. Sorry, give me a second. Okay, so I'll leave you to practice that. And let's go back to finishing our lesson. Loading, loading, loading. Here's a summary of everything that we've learned today.
What I want to do in this video is give an introduction to the language or some of the characters that we use when we talk about geometry. And I guess the best place to start is even think about what geometry means. As you might recognize the first part of geometry right over here. You have the root word geo, the same word that you see in things like geography and geology. And this refers to the earth. This refers, my E looks like a C right over there. This refers to the earth. And then you see this metry part, and you see metry in things like trigonometry as well, and metry, or the metric system, and this comes from measurement. This comes from measurement, or measurement. So when someone's talking about geometry, the word itself comes from earth measurement, and that's kind of not so bad of a name because it is such a general subject. Geometry really is the study and trying to understand how shapes and space and things that we see relate to each other. So, you know, when you start learning about geometry, you learn about lines and triangles and circles, and you learn about angles, and we'll define all of these things more and more precisely as we go further and further on, but also encapsulate things like patterns and three-dimensional shapes. So it's almost everything that we see, all of the visually mathematical things that we understand can in some way be categorized in geometry. Now with that out of the way, let's just start from the basics, a basic starting point from geometry, and then we can just grow from there. So if we just start at a dot, that dot right over there, it's just a point. It's just that little point on that screen right over there. We literally call that a point, and I'll call that a definition. And the fun thing about mathematics is that you can make definitions. We could have called this an armadillo, but we decided to call this a point, which I think makes sense because it's what we would call it in just everyday language as well. That is a point. Now what's interesting about a point is that it is just a position, that you can't move on a point. If you were at this point and if you moved in any direction at all, you would no longer be at that point. So you cannot move on a point. Now, there are differences between points. For example, that's one point there. Maybe I have another point over here, and then I have another point over here, and then another point over there. And you want to be able to refer to the different points, and not everyone has the luxury of a nice colored pen like I do. Otherwise, they could refer to the green point or the blue point or the pink point. And so in geometry, to refer to points, we tend to give them labels, and the labels tend to have letters. So for example, this could be point A, this could be point B, this would be point C, and this right over here could be point D. So if someone says, hey, circle point C, you know which one to circle. You know that you would have to circle that point right over there. Well, that so far it's kind of interesting. You have these things called points. You really can't move around on a point. All they do is specify a position. What if we want to move around a little bit more? What if we want to get from one point to another? So what if we started at one point and we wanted all of the points, including that point, that connect that point and another point. So all of these points right over here. So what would we call this thing? All of the points that connect A and B along a straight, and I'll use everyday language here, along kind of a straight line like this. Well, we'll call this a line segment. In everyday language, you might call it a line, but we'll call it a line segment, because we'll see when we talk in mathematical terms, a line means something slightly different. So this is a line segment. And if we were to connect D and C, this would also be another line segment. A line segment. And once again, because then we always don't have the luxury of colors. This one is clearly the orange line segment. This is clearly the yellow line segment. We want to have labels for these line segments. And the best way to label the line segments are with its endpoints. And that's another word here. So a point is just literally A or B, but A and B are also the endpoints of these line segments because it starts and ends at A and B. So let me write this. A and B are endpoints. Another definition right over here. We could have called them aardvarks or end armadillos, but we as mathematicians decide to call them endpoints because that seems to be a good name for it. And once again, we need a way to label these line segments that have the endpoints. And what's a better way to label a line segment than with its actual endpoints? So we would refer to this line segment over here. We would put its endpoints there. And to show that it's a line segment, we would draw a line over it just like that. This line segment down here, we would write it like this. And we could have just as easily written it like this. CD with a line over it would have referred to that same line segment. BA with a line segment, with a line over it, would refer to that same line segment. Now you might be saying, well, I'm not satisfied just traveling in between A and B. And this is actually another interesting idea. When you were just on A, when you're just on a point and you couldn't travel at all, you couldn't travel all in any direction while staying on that point, that means you have zero options to travel in. You can't go up or down, left or right, in or out of the page and still be on that point. And so that's why we say a point has 0 dimensions. 0 dimensions. Now all of a sudden we have this line segment here. And this line segment, we can at least go to the left and the right along this line segment. We can go towards A or towards B. So we can go back or forward in 1 dimension. So the line segment is a one-dimensional idea almost, or a one-dimensional object, although these are more kind of abstract ideas. There is no such thing as a perfect line segment because a line segment, you can't move up or down on this line segment while being on it. While in reality, anything that we think is a line segment, even a stick of some type, a very straight stick, or a string that is taut, that still will have some width. But the geometrical pure line segment has no width. It only has a length here. So you can only move along the line, and that's why we say it's one-dimensional. A point, you can't move at all. A line segment, you can only move in that back and forth along that same direction. Now, I just hinted that it can actually have a length. How do you refer to that? Well, you refer to that by not writing that line on it. So if I write AB with a line on top of it like that, that means I'm referring to the actual line segment. If I say that, let me do this in a new color. If I say that AB is equal to 5 units, it might be centimeters or meters or whatever, or just the abstract units 5, that means that the distance between A and B is 5, that the length of line segment AB is actually 5. Now let's keep on extending it. Let's say we want to just keep going in one direction. So let's say that I started A, let me do this in a new color. Let's say I started A, and I want to go to D, but I want the option of I want to keep on going. So I can't go further in A's direction than A, but I can go further in D's direction. So this idea that I just showed, essentially it's like a line segment, but I can keep on going past this endpoint. We call this a ray. And the starting point for a ray is called the vertex. Not a term that you'll see too often. You'll see vertex later on in other contexts, but it's good to know. This is the vertex of the ray. It's not the vertex of this line segment, so maybe I shouldn't label it just like that. And what's interesting about a ray, it's once again a one-dimensional figure, but you could keep on going in you can keep on going past one of the endpoints. And the way that we would specify a ray is we would call it AD, and we would put this little arrow over on top of it to show that it is a ray. And in this case, it matters the order that we put the letters in. If I put DA, if I put DA as a ray, this would mean a different ray. That would mean that we're starting at D and then we're going past A. So this is not ray DA, this is ray AD. Now the last idea that I'm sure you're thinking about is, well, what if I could keep on going in both directions? So let's say I can keep going in, my diagram is getting messy. So let me introduce some more points. So let's say I have point E and then I have point F right over here. And let's say that I have this object that goes through both E and F, but just keeps on going in both directions. This is, when we talk in geometry terms, this is what we call a line. Now notice, a line never ends. You can keep going in either direction. A line segment does end. It has end points. A line does not. And actually a line segment can sometimes be called just a segment. And so you would specify line EF. You would specify line EF with these arrows just like that. Now the thing that you're going to see most typically when we're studying geometry are these right over here, because we're going to be concerned with sides of shapes, distances between points. And when you're talking about any of those things that have finite length, things that have an actual length, things that don't go off forever in one or two directions, then you're talking about a segment or a line segment. Now, if we go back to a line segment, just to kind of keep talking about new words that you might confront in geometry, if we go back talking about a line, I was drawing a ray. So let's say I have point X and point Y. And so this is line segment XY. So I could specify it, denote it just like that. If I have another point, let's say I have another point right over here. Let's call that point Z. And I'll introduce another word. X, Y, and Z are on the same, they all lie on the same line, if you would imagine that a line could keep going on and on forever and ever. So we can say that X, Y, and Z are collinear. So those 3 points are they are collinear. They all sit on the same line, and they also all sit on line segment XY. Now let's say we're told that XZ is equal to ZY, and they are all collinear. So that means this is telling us that the distance between X and Z is the same as the distance between Z and Y. So sometimes we can mark it like that. This distance is the same as that distance over there. So that tells us that Z is exactly halfway between X and Y. So in this situation, we would call Z the midpoint of line segment XY, because it's exactly halfway between. Now to finish up, we've talked about things that have 0 dimensions, points. We've talked about things that have 1 dimension, a line segment, or a ray. You might say, well, what has 2 dimensions? Well, in order to have 2 dimensions, that means I can go backwards and forwards in 2 different directions. So this page right here, or this video, or the screen that you're looking at, is a 2-dimensional object. I can go right, left, that is 1 dimension, or I can go up, down. And so this surface of the monitor you're looking at is actually 2 dimensions. 2 dimensions. You can go backwards or forwards in 2 directions. And things that are 2 dimensions, we call them planar, or we call them planes. So if you took a piece of paper that extended forever, it just extended in every direction forever, that in a geometrical sense was a plane. The piece of paper itself, the thing that's finite, and you'll never see this talked about in a typical geometry class, but I guess if we were to draw the analogy, you could call a piece of paper maybe a plane segment, because it's a segment of an entire plane. If you had a 3rd dimension, then you're talking about kind of our 3-dimensional space. In 3-dimensional space, not only could you move left or right along the screen or up and down, you could also move in and out of the screen. You could also have this dimension that I'll try to draw. You could go into the screen, or you could go out of the screen like that. And as we go into higher and higher mathematics, although it becomes very hard to visualize, you'll see that we can even start to study things that have more than 3 dimensions.
All right, so we've gone over this several times now. Hopefully you get the concepts of today. Let's test it out. Let's see what you got here. So your objective is to do this progress check once it loads. So it's got 8 questions in it. It's 20 questions. It's posted on Google Classroom. Okay, show me you have learned the concepts from today. Now the last part, your assignment, is discussion posts. Okay, so I've posed a question on Google Classroom. Your objective is to post and reply. So let me say that one more time. You need to make a post yourself, and you need to reply to someone else's. So go ahead and pause the video right now so you can look at the rubric for how I'm going to grade this. But your question is, are skew lines and parallel lines the same? Why or why not? Give a real-life example of skew lines and a real-life example of parallel lines. Make sure your answer is unique from your classmates. So you need to go to that post on Google Classroom and answer this question. Then, once more people have responded, you need to go reply to someone else. Okay? Again, here's the rubric. Take a look. That's it for today. So let me show you on Google Classroom. Here's everything from today, except for the video that I'm filming right now. So part 1, it's already up. You need to do the attendance question for the week. Here's your first practice. Then you're going to make your Venn diagram. Right here is where I'll put the video number 2. Then you need to, then I'll also put the practice for the skew lines. Here's your progress check and the discussion question. Okay, that's it. There's the whole week of assignments. Good luck. Message me on Google Hangouts if you have any questions. I'm here to help. Love to sit down with anyone in office hours if you need it. Let me know. Thanks. Bye.